Hello, this is Erica Gulston. Today we'll be talking about constant velocity. All right, after a brief introduction, we'll walk through the physics concepts and models, the experiment and the code used in the models, and the discussions and conclusions we can draw based on the data. All right, so for our introduction, the purpose of this experiment is to study constant velocity and how that will reflect in position. So we're going to graph position versus time and see how the constant velocity affects that graph. The physics principles that we'll be studying are Newton's first and second laws, which relate net force, constant velocity, and the relationship between those two things and the position of an object. All right, so to walk through the physics concepts and models, the biggest thing here is going to be Newton's laws. So this Newton's first law says that unless a net force is applied to an object, the object's velocity will remain constant. So it will either remain at rest or in motion, aka zero acceleration, aka zero change in velocity, meaning constant velocity. So when an object is at constant velocity, the object will travel the same distance with each time interval. The position versus time graph of the object, therefore, should be linear at a constant velocity because it is traveling that same distance every time. All right, so for the experiment itself, what we did was push an object and then allow it to roll at constant velocity. So as can be seen in the video, a force was applied, but then after that force was applied, the net force on the object was zero and it was just allowed to roll. So when graphed, that object should travel the same distance each time interval. The video link is here in case anyone would like to see. And we used a video tracking software in order to track the motion of that object. So as we can see, in the x direction, the motion of the object was fairly constant. It's moving about the same distance with every time interval. The chosen interval was 1/30th of a second. So as we can see, that distance is pretty constant, reflecting that constant velocity after that first net force. All right, so we did a computational model using GlowScript. And as you can see, the generated model also moved in a linear motion. So we used the initial velocity from the video tracking software as the constant velocity in the model. And then we used the code to update the position and the velocity at each time interval, again, 1/30th of a second. And that GlowScript code is also linked. An example of the code here, this is pulled directly from GlowScript, just removing the comments for clarity. As you can see, the net force is zero, and the ball's velocity will remain constant because of that zero net force, which means that when we update the position here, the ball's position will just update by increments of that velocity with every time interval. So when we graph that, that means that the motion of the object should just remain linear and increasing by a constant slope, which should be the velocity. So let's see if that's true. All right, so when we graph the data, it lines up pretty well. The observed x position and the predicted x position are both fairly linear. The predicted is obviously a little perfect, and the observed has like slight deviations. So we'll explain why that's the case in a second. But as you can see, our hypothesis was correct that at constant velocity, the motion of this object will be linear and will be increasing by an even amount with each time interval. So those error sources are going to be environmental forces and human error. So the system is the object and the surroundings is everything around it. And those surroundings have forces that are acting on the object. So air resistance and friction are there in the real world. And our computational model unfortunately can't account for those. There also could be human error when using the tracking software and selecting those points. There could be slight discrepancies in the distances. Let's look at our conclusions. So to answer some big questions, please pause and read the questions if needed. But if the axes were switched, the motion would not necessarily change, but the direction of the motion would. So as we can see, we're moving in the negative x direction in all of our models. But if we switch the axes, we'd have the movement by the same magnitude, but just in the positive direction instead of the negative. So just the signs would switch, but the values would remain the same. When we're talking about how many forces are acting on the object, because in the real world, we do have to consider all of those. In the y direction, we have the gravity force and the normal force that are canceling each other out, making that zero net force in the y direction. In the x direction, we have the initial push, and then we have the friction force and the air resistance that are acting in the opposite direction of that. So ideally, the net force should be zero after the push, But friction and air resistance in the real world will change that, and the object will eventually come to a stop. But the motion that we observed was fairly constant because friction and air resistance weren't canceling out that initial force yet. All right, thank you for watching, and um, thank you for this interpretation of constant velocity.